This is a short video on Pauli spin matrices. Okay, so I'm going to make this as brief as possible because this can be very useful for a general chemistry audience, and that's who this is targeted towards. But there's a lot of material you can get bogged down with, so I'll try and go through the weeds a little bit and get to the meaty stuff. So let's start off by writing the Pauli matrices. So spin matrices, sigma in the x-axis is h bar over 2, 0, 1, 1, 0. Sigma in the y-axis is h bar over 2, and then the matrix 0, minus I, 0. And then finally, sigma in the z-axis is h bar over 2, 1, 0, 0, minus 1. Okay, I see no point in memorizing those, so I would just assume that you would have access to them. Obviously, if you do them as a career, you won't be able to forget them, but I think it's personally a waste of time if you're just going to take one exam and never look at them again to bother memorizing them. Okay, notice they all have factored out h bar over 2. You can look at my video on simple harmonic oscillators to have a feel for where that h bar over 2 comes from. So essentially we're going to ignore that h bar over 2 when we do a little bit more, when we do the following. So what we're going to do is we're going to find eigenvalues of these matrices. So we're going to find what are called eigenvalues of these Pauli matrices. Now you can also find, and you should by all means, find the eigenvectors. That's a bit more complicated, and it would definitely likely double my video length, so I would separate that as another video. And also, as a tip for anyone learning this for the first time, I would suggest you focus on the eigenvalues because they're so much easier, in my opinion, than the eigenvectors, at least quicker. So to find the eigenvalues, essentially these are the values that these Pauli matrices can provide. We take, well, I'll write it down and I'll explain what it means. We take the determinant of this expression, sigma, where sigma could be sigma x, sigma y, or sigma z, minus lambda I, and we set that equal to 0. And then essentially we solve for lambda. So if I can change the color of this pen to red. Yeah, so the eigenvalues would be lambda values here. I is the identity, which we'll see what that is in a second, and I'll show you what determinant means in a second. There's a lot of jargon, if we're going to be very rigorous, which we're not. There's a lot of jargon that I'll avoid in this video, like operators, etc., and hats that we can spend all day worrying about. But we're not going to bother with that. We're just going to get to the basic operation of how this thing works. Okay, so we're going to try and solve for lambda, and we'll do them one at a time. So let's pick x first, I guess. So let's focus on, for the Pauli matrix sigma x. Okay, then we have the determinant. Don't worry what the determinant is yet, but let's write down sigma x So we've got 0, 1, 1, 0. That's the Pauli matrix for sigma x. And then minus lambda, the identity. The identity, I'll write down here, the identity is just 1, 1, 0, 0. So if I multiply through by lambda I, then every time I have a 1 in my matrix and lambda hits it, I get lambda. So that just becomes lambda, lambda, 0, 0. Okay? So then I just subtract these two matrices. So I have the determinant, which I still haven't explained what that is yet. Then I've got 0 minus lambda, which is just minus lambda. Then I've got 1 minus 0, which is just, excuse me, 1. Obviously 1 minus 0 is 1. Then I've got 1 minus 0, which is just 1. And 0 minus lambda, which is minus lambda. Okay, so take the determinant of this and set it equal to 0. Well, now we can see what the determinant is, or how to do it at least. So the determinant essentially for a matrix ABCD is the cross, the subtract, I'm trying to think the right way, well, not the right way, a reasonable way to say it. It's the diagonals subtracted from each other, so AD minus CB. So AD minus CB. Okay. So that's the determinant of a 2 by 2 matrix. If we apply that to our situation here, then we just have minus lambda minus another lambda, which is just lambda squared, minus 1 minus 1, minus lambda multiplied by minus lambda, which is minus squared, minus the product of 1 multiplied by 1, which is 1, and we set that equal to 0. Okay? If we take the 1 to the other side, we have lambda squared is plus 1, and therefore we know that lambda could be plus or minus 1. If lambda squared is 1, we take the square root, we could have plus or minus 1. Okay, so there's our result. So this is the eigenvalues of the Pauli sigma x spin matrix. Remember that we do have the factor of h bar over 2. So we can have, essentially, if we put the two values in, so let me write it, otherwise I'll forget. So sigma x gives plus 1 multiple of h bar over 2 and minus 1 multiple of h bar over 2. Okay, so that's what it means. Okay, let's have a look for, we'll do the same thing and I'll try and get a move on, lots to do. Let's do the same thing for sigma y. So for sigma y, then we've got the determinant of the Pauli matrix sigma y, which is 0 minus I 0, minus lambda the identity, which we now know is just lambda lambda 0, 0. And that's just going to be the determinant of 0 minus lambda, which is just minus lambda, minus I minus 0, which is just minus I. And then we have I minus 0, which is I. And then we have 0 minus lambda, which is minus lambda. Set that equal to 0. So for the first time we're seeing I here, so we should probably, well, we'll point out what I is, I guess. That would be, I was going to point it out later, but it's snuck up on us 11 minutes in. So it doesn't matter what I is, but let I, it doesn't matter where it comes from. You can see one of my other videos for that. But by definition, I is the square root of negative 1, or you could say that I squared is negative 1. So these are just, well, it's basically the same definition, depending on how you want to think of it. Okay. So if we calculate this, it implies, so we're going to take the diagonals, we're going to subtract the diagonals. So minus lambda, that's just lambda squared. And then we're going to take, from that, we're going to subtract the product of I and I. So that's just going to give us 1 again. And then we set that equal to 0. So we can say that lambda squared, as before, is equal to 1. And we can therefore say that lambda is therefore plus or minus 1. And just as we saw with sigma x, we know that sigma y has values, eigenvalues. We put the h bar over 2 back in. We've got plus h bar over 2, so that's the plus 1 multiple of h bar over 2, and minus the 1 value, which is minus h bar over 2. Okay, and finally, although you probably don't need it now because it's repetitive, let's do sigma z. Okay. So for sigma z, we've got the determinant of 1, 0, 0 minus 1 minus lambda of the identity, which is this 2 by 2 matrix. That's therefore the determinant of 1 minus lambda, one minus 0, which is 0, 0 minus 0, which is 0, and then minus 1 minus lambda. We set that equal to 0. Okay. So if we actually do this, we've got 1 minus lambda multiplied by minus 1 minus lambda, and then we've got to subtract from that 0 multiplied by 0. And we set that whole thing equal to 0. Okay, see how much space I've got? Alright, got plenty of space. Okay, which implies that, well, we've got to FOIL this out. So we've got 1 multiplied by minus 1. So I'm going to FOIL this out. So the first, then the outer, then the inner, and then the last. Okay, so we'll FOIL it out. So the first is 1 by minus 1, which is just minus 1. And then plus we have outer, which is 1 by minus lambda, which is minus lambda. And then inner, we have minus lambda multiplied by minus 1, which is plus lambda. And then last, we have minus lambda by minus lambda, which is plus lambda squared. Okay? Subtract 0 equals 0. Okay. So let's have a look what we have. Well, I've got plus and minus lambda, so they cancel. So I'm left with lambda squared minus 1 is 0, as I have been all along. So lambda squared is plus 1. Or I can just write 1, can't I? I guess to be consistent, I don't need to write the plus. So lambda is plus or minus 1. So like the other Pauli matrices, sigma z can have two values, two eigenvalues. You can have plus h bar over 2 for the plus 1 multiple of h bar over 2, and you can have minus h bar over 2 for the negative 1 multiple of h bar over 2. Okay, so that's the. Let's summarize what we have. Okay. Actually, I think we have just summarized what we have. Yeah, let's write this. It's common to report spin in the z-axis. So if this represents sigma in the z-axis, then we have, let's see if I can get this done in a reasonable amount of time. Then we can have plus h bar over 2, we can have minus h bar over 2, and often the one that's up you typically call alpha, the one that's down you typically call beta. Notice as well that these are order of magnitude h bar apart. And we typically, alpha, when you write electronic orbitals, you typically write alpha as a spin up, a spin plus a half electron, and it's convention to write beta as a spin negative a half electrons. So this is when you're looking at atomic orbitals. Okay, That's all I wanted to say about that, just to bring it in. Again, I have another video on this, so I don't want to overlap too much, but this would link it into another video where I look at quantum numbers. Okay, so we know, if we look at where we've come from, we were looking at Pauli spin matrices. We've calculated the eigenvalues only. We haven't bothered with the eigenvectors, which would double or triple the length of the video, which would make 99% of people not watch. So in an effort to keep this short and sweet, this is my path of least resistance. We've seen that the electron can have two eigenvalues, and it's plus or minus one multiple of h bar over 2. Okay. Let's make sure I've got enough pages left for what's to follow. So I've got 1, 2, 3, 4 pages left. Let's see if that's going to be enough. I need 1. Yeah, that should be enough. Okay, that's perfect. Okay, so the following are just some statements. And again, I wouldn't expect any of my students certainly to memorize these. But we're just going to set up useful stuff. It's just going to be useful. Okay. So I'm going to start by saying let up, so spin up, imply up. I'm going to symbolize it with this U in a ket. So this line with the back wedge here is called a ket. And it implies we're in the plus z direction if we look at our Cartesian axis. This would be plus z, negative z would go down. This would be plus x, negative x would go that way, and this coming in and out of the plane would be plus y, negative y, let's say, would go into the board. or vice versa, it really doesn't matter. You know plus, you know the opposite is minus. Okay, let down be symbolized by d, and that's the minus z. Let O mean out, and let's say actually, if I'm going to be consistent, now I've got to call this minus. If I'm going to be consistent, then out is going to be minus y. And in would be plus y into the board. Let I in this ket mean in, and that's plus y. Let R imply right, and that's plus x, because that's to the right. And let L mean left, and that is minus x. Okay, so useful stuff. If we have all of that, and there's also some extra stuff that we can mention, then we're going to make some assertions and then we'll verify a couple of them. So I'm just going to make some assertions and then we'll verify them. We're going to assert that the bracket out, up, you may or may not have any idea what I mean when I say bracket. but that's okay. Nobody knows until somebody tells them, right? So I'm going to be that someone. The bracket, or the product of brackets, a bracket is this whole thing here. So essentially, this thing is a bra. This thing is a ket. And we have a bracket. Again, this thing is a bra. This thing is a ket. So we have two brackets. We multiply them together. That's a product of brackets. Okay. So this product is a half. This product, out, down, down, out, is also a half. And what I mean by a half here, whenever you take the product of a bracket, this is a probability. Okay, so essentially what we're going to show is that if you have an electron that's in, ultimately, I'll give you a sneak peek of what I'm ultimately going to tell you. So we know this up, down, left, right, in, out is really X, Y, and Z, right? If I've got an electron oriented in up in the plus Z orientation, we're going to show that if you know its orientation in the z-axis, you have no information about its orientation in the x or y plane. Okay, and we're going to show that by calculating the probability, and if the probability is a half in the plus x and the minus x, then you know nothing about which orientation it's in because you know it's 50-50. So a half here means 50% knowledge, which essentially means you know as much as you don't know, so you essentially know nothing. So it's 50-50, you know nothing. All right. Let's go for in and up and in. That's a half. In and down. Down and in. That's a half. Out and right. Right and out. That's a half. Out and left. Left and out is a half. In and right. Incidentally, when you look at this, don't worry. My advice is anyone looking at this for the first time, don't worry about why it is like this for now. Worry about how to do it. I think a mistake is to worry about, it's not something that you can see in your mind's eye. It's an abstract notation that works. And without getting bogged down in that discussion, which is a whole nother video, the way to get most bang for your buck is just to know how to follow the steps and worry little about why the steps are the way they are. Okay, there's some information I want you to know in addition to this. So I'm just going to say also, I'll try and box this off. So also know this, if we have a bracket which has the same bra and ket, so remember the bra is on the left, the ket is on the right, a bra and a ket which are the same is equal to 1. However, a bra that's not equal to the ket is equal to 0. Another thing I want you to know that we'll need, if we have the ket x, and let's say it's equal to I, y, then if we make that ket into a bra by flipping it round, we have to change the sign of I. So minus I, y. And again, I want to remind you that I is the square root of -1. Okay, doesn't matter why all of this stuff, that's another video, but just accept that. We're going to use that for now. And also, we're going to write down the following that we'll need. So this page is stuff we'll need. Right is 1 over root 2 up plus 1 over root 2 down. Left ket is 1 over root 2 up minus 1 over root 2 down. In is 1 over root 2 up plus I over root 2 down. And finally, out is 1 over root 2 up minus I over root 2 down. Okay, so this page, this is like the cheat sheet if you like. This is what I would have in front of you when you're going to try and recreate the following. All right. So I don't think there's any point memorizing that. That's just stuff. You're a mechanic. That's a bag of wrenches. Okay, you can't work on a car without your bag of wrenches, right? So what I'd like to do now is just pick out a few examples of these to see why knowledge of the spin in one orientation renders you incapable of knowledge in any other orientation. So I'm going to try and show these probabilities are half and just learn how to manipulate some of these numbers. Okay, so the first example I want to look at is this one. Out, up, up, out. We want to show that that's equal to a half. Okay, so let's write down the stuff we'll need. So let's write down the bra. The bra out is 1 over root 2 up plus I over root 2 down. And the ket out is 1 over root 2 up minus, remember the bra and the ket, you change the sign of I, minus I over root 2 down. So if you look in the previous slide, the bottom one, the ket out, is the one I gave you here. I got the bra out by changing the sign of I to make it positive. Okay, and I did that, I wrote that down to make it easier because I've got the bra out and the ket out. The bra and the ket up, we're just going to write U for up. Okay. All right, so let's do the first product. So I'm going to solve for the product of the bracket out, up. Well, that's equal to this thing here. And I can see that I'm going to multiply each term by the ket up. So I've got this coefficient 1 over root 2. Then I've got my bra up, which hits my ket up. Then I've got to add a second term. I've got I over root 2, and then I've got my down bra, which hits my up cat. Okay. Now remember from our cheat sheet page that when the bra and the cat are the same, it equals 1, and when the bra and the cat are different, it's 0. Okay. So that means that this bracket is equal to 1, but this bracket is equal to 0. And the 0 means that this term disappears. All right. So this implies that the bracket out up is equal to, the only thing that survives is this coefficient here, 1 over root 2. All right. So we've done the out up. We've done the out up bracket. Now let's look at the up out bracket or bracket. Okay, so let's look at up out. Well, that equals 1 over root 2 up, and then I hit the out with that. Which is u minus I over root 2. Again, my bra comes in and hits my down here. Okay. So I know that because this bra, that's funny, I've just hit, that was funny, I hit the wrong tab, that's why. I wondered why my screen disappeared then. I hit the text color. So we know that this is equal to 0 because they're different. This is equal to 1 because they're the same, so this term disappears. So I know that the bracket up, out is just equal to the coefficient 1 over root 2. Okay, so now I've got both. I can take the product of them. So this implies that the product of brackets out, up, multiplied by up, out, is equal to 1 over root 2 multiplied by 1 over root 2, right? Because on both occasions I had 1 over root 2. Well, this just equals 2 over root 2, which is equal to 1/2, which is exactly what we tried to show in the first place. So this is just to give you a taste of how to use this type of mathematics, which ultimately is the simplest language to write it in. It gets complicated when you try and translate it into something that's more familiar. You may as well use it in this language. Okay, so that's one example. I'm not going to do all of these examples, but rest assured they all equal 1/2. Let's do another example. So I think we can do more than one example without losing the crowd. Let's do in, down, down, in, and we'll see that that's equal to 1/2. Okay, let's write in. The bra in is 1 over root 2. The bra up minus I over root 2, the bra down, and that's because the ket in is 1 over root 2, the ket up plus I over root 2, the ket down. This is the one I gave you, so you have to reverse all the kets to bras, and then you change the sign of I. Okay, so we've got the bra and the ket, and every time we see D, we just write D. So let's look at the first bra-ket product, which is ID. So ID is equal to 1 over root 2, and then we have this up, the bra up is going to hit, it's going to hit D because we're multiplying this term by D. So it's going to hit D, and then we're going to subtract from that minus I over root 2, and then this D is going to hit, this bra D is going to hit the ket D. The bra and the ket are the same, so this term equals 1. The bra and the ket are different, this term equals 0. So therefore this whole term disappears. And we know that the product in down is equal to 1 multiple of this coefficient, which is minus I over root 2. Okay? Let's continue and look at the other bra-ket product, the DI. Okay, so let's do DI. Well, we've got down, which hits the ket I. So from the ket I, we have the coefficient 1 over root 2. Then we have the down bra, and then it hits the up ket plus I over root 2. Then we've got the down bra again, hits the down ket. Bra and ket are different, equals 0. Bra and ket are the same, equals 1. So this term on the left disappears. So this implies that the bra ket down in equals plus I over root 2. So now we're in a position to look at the final product of both brackets. Okay, so this implies that in down, down in equals minus I over root 2 plus I over root 2, which equals 1 over 2, which is what we said it would, but we've learned how to operate the math. And you can go back and pause this video, obviously, and have a look. So not too bad, not too difficult, maybe unfamiliar, but as I say to my students, don't confuse hard with unfamiliar. Just very, very unfamiliar. But fortunately, we didn't have to figure this out. We can just learn from people that figured this out. So there's two examples of what happens when you change the basis. So again, I'm trying to avoid the technical jargon, which I think can drown out the message. So essentially, if you go from in to down, or you change the basis to introduce a little bit of jargon, you lose information. What if you don't change the basis? So this is going to be my final example. and mercifully it's easier, or quicker. Easier is relative. Quicker is universal. It's quicker than the other bit. What if you had up, 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 or down, 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 or what have you? Okay. So what if you put the electron in spin up state and then you measure it again in the spin up state? Well, this will equal 1. So essentially, if these are the same, it's always going to be equal to 1. And you know that trivially because we've said already, bra and ket are the same, it's 1. Bra and ket are the same, it's 1. So the product is just 1 multiplied by 1, which equals 1. Okay. So that pretty much wraps up this video. So again, we've just had a look at Pauli spin matrices. We saw that Pauli spin matrices have eigenvalues of plus or minus 1 multiple of h bar over 2. We looked at that for sigma x, sigma y, and sigma z. Then we pretty much went on to some useful stuff, and we started looking at probabilities. If I have an electron that I know is up, what if I measure it as up again? Will it be up again? Yes, you've just seen if it's up and you measure it up again, it will be up with 100% probability, or a probability of 1. However, if you measure it up and then you measure it again in a different basis, you lose information. You therefore, with 100% information on the basis you set it to, measuring it in another basis, you don't have any knowledge. You have half probability of it being in or out, or up or down, or left or right. That's what these halves were. These were probabilities, and without duplicating another video, probability is the product of two brackets. And we had a look at some examples here. We introduced some new bracket notation without any jargon, absolutely jargon free as much as possible. And then we saw just by following the math, you get some nice half probabilities that come out, which is exactly what we wanted to. So hopefully this will be useful to my students in general chemistry.